Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to look at linked lists with dynamic memory allocation. So in this topic, we will describe how to create a linked list using addresses. That is, we are going to start using dynamic memory allocation, and the next pointers will be addresses, not indices. We will learn how to add, access, and remove nodes from such a linked list. We will do all of this while ensuring that we do not have any memory leaks. We will then look at other functions, member functions that could be implemented on a linked list, and we will see how these member functions can loop through the nodes in a linked list. We will then see how friendship can be used to allow access to private member variables by functions that are not declared as member functions, but nevertheless need access to the appropriate private member variables when necessary. Now, in the last topic, we introduced the following class for a node. So in that topic, the linked list was of the form where all nodes were stored in an array. Each node stored a value and the index of the next node. And we required one local variable to store the index of the first node, that is, the head of the linked list. Now, suppose instead we dynamically allocate memory each time we require a new node. So basically, if we require a new node, rather than finding an unused node in the array, we just call new node with appropriate arguments. Consequently, we will be able to address that node not with an index, but with the address returned by new. Consequently, we will be storing the address of the next node. So rather than having an index as a second member variable, we have a pointer to a node. That is, we will be storing the address of the next node in the linked list. Now, if every single node is storing an address instead of an index, then what we need is a local variable that stores the address of the first node. So here is that local variable. Then what we will be doing is that address, that local variable, will be storing the address of the first node. The first node in its pointer to next node member variable will store the address of the second node. The second node will store the address of the third, and so on and so forth. The last node in the linked list will have as its next node the address null pointer. Now, in a sense, these two classes aren't that different. In the first, we had an array of possible nodes, and we stored the index of the next one. Well, in the second, you can just think of memory as essentially a very large array, and the address is simply an index into that array. So these two designs are not that different. The only difference really is that in the first case, in the last topic, we created all the nodes initially using a local array, whereas now the operating system will be giving us the memory for each additional new node. Now let's expand on this node class. Of course, at the bottom here we have our two private member variables. We're going to have a constructor, and the constructor will simply assign those two private member variables whatever the constructor is passed. We then have two member functions that allow us to access the two private member variables and two member functions that allow us to assign to those two values. Now, for this class, it's going to be very straightforward, but nevertheless, this is a reasonable design. So here the constructor simply assigns both member variables the two arguments that are passed. The member function return returns the value, as does the member function pointer to next node. We can set the value, and at this point we're not going to check what the user passes to us, and we are going to also allow the user to set the next node as well. In the last topic, you'll recall that we required one local variable to store the index of the first node in the linked list. Well, in this case, since we are now storing addresses instead, we require a single local variable that stores the address of the first node in the linked list. So here we have a figure representing the list head local variable. It's initially set to null pointer. However, as we go on, we may be adding more and more new nodes to this linked list. So the list head will store the address of the first node. The first node will store the address of the second node. The second node stores the address of the third node, and so on and so forth. Consequently, as long as we are storing the address of the first node, we indirectly have access to every single node in this linked list. The problem is, if the pointer to the list head is a local variable, that means that a user may accidentally assign to that local variable, say, null pointer. So all of a sudden, we have lost the address of the first node in the linked list. And so while the first node still has the address of the second node, and so on and so forth, if we don't have the address of the first, we cannot access any of the others. So consequently, we have the potential for a very large memory leak if we accidentally assign pointer to list head the wrong value. Now, the fact that the user accidentally assigning to the local variable pointer to list head may cause us to lose the addresses of all of the nodes in the linked list suggests strongly we too should place this variable into a class. So here we have a linked list class, and its only purpose is to store the address of the first node in any linked list. Now, when we create a linked list, we're assuming there are no nodes in that linked list at this point. Consequently, the constructor will do nothing more than assign the member variable the value null pointer. In this class, each of the nodes will be created using dynamic memory allocation. And as suggested previously, any class that deals with dynamic memory allocation, such as the array class, likely requires a destructor to potentially clean up memory if a linked list ever goes out of scope or is deleted. Now, next here we have the copy constructors, the assignment operators, the move constructor, and the move operator all assigned to delete. This prevents the user from accidentally copying or assigning one linked list to another. We will, however, have two member functions. Now, in a linked list, we will refer to the first node of the linked list as the front of the linked list. assuming, of course, that there is at least one. So the member function front will return whatever value is stored in that first node. The member function push front will take as an argument a new value, and that member function will create a new node and put that new node at the current front of the linked list. So what used to be the front node will now become the second node in the linked list. So as far as defining the constructor, it doesn't take any arguments, and it simply assigns list head the value null pointer. We're going to define the destructor, but we're not going to implement it yet. We'll worry about the implementation later once we understand how the linked list is being constructed and manipulated. However, we do need to at least define an empty destructor at this point, otherwise it will not compile. Let us assume that we have an array of these nodes. In this case, we could identify each node with the index at which it is in the array. So this would be a value between 0 and capacity -1. So rather than a student remembering the name of the next student in the linked list, we will store the next index within the linked list, and this will be a value between 0 and capacity -1. Thus, we could store our nodes as follows. We could have a capacity that is fixed, say 10, and then we create an array with that many nodes. Now, we will initialize everything to 0. However, we need some way of indicating that currently none of these nodes are being used. We will indicate that a node is not being used by setting its next index to the capacity +1. So in this case, that would be 11. So if the next index is 11, that indicates that that node is currently not being used. So initially we have 10 nodes, none of which are being used for our linked list. Now, to remember a linked list, just like I only had to remember the name of the first student, the program only has to remember the index of the first entry of that linked list. So all the program has to remember is one index. We will call that index list head. And to indicate that there are no nodes in this linked list so far, we will set list head to be the capacity of the array. Now, when the linked list is going from having no nodes to having exactly one node, initially the linked list is pointing to the null pointer. What we have to do is we have to initialize the first node. So the first node is storing the value we want stored, but also that first node is also now pointing to null pointer. However, we then have to update the linked list to store the address of that first node. Let's do that. So this is what we're starting with. Here we see the linked list class. It has one member variable pointer to list head, and it is initially assigned 0, that is the null pointer. What we want to do is we want to get to this point where we have dynamically allocated a node, set its value to whatever we're trying to store. It should be storing as pointer to next node the null pointer, but we want to assign to list head the address of this new node. So how are we going to get to this point for this linked list? Well, right now we're only dealing with a case when the list head is assigned null pointer. That is, the linked list is empty. Well, we want to create a new node and it should be storing our new value. So here we call new node and we pass it the new value we want to store, and its next pointer or next node member variable should be set to null pointer. So we will temporarily store this address in a local variable pointer to new node. So we now have a pointer or a local variable storing the address of this new node. Well, all we have to do now is set the list head to be this address. Okay, that's it. Now let's add one more value to the front of this linked list. So we've pushed 4.2, now we want to push 9.1. Now, if we are adding a new node to the front of the linked list, it really doesn't matter whether or not the linked list currently has one node in it or more than one nodes in it, because the act of adding a new node to the front of the linked list really only affects the list head. So it doesn't matter whether or not we are adding a new node when there's only one node in that linked list, or if there's two nodes, or if there are more than two nodes. The act of adding a new node simply will have us change the list head member variable of the linked list class. We may need access to the other nodes, but we actually only will need access to that first node in the existing linked list. So this is what we're starting with. List head is storing the address of the first node in the linked list. If we want to push a new node into that linked list, this is what we want to end up with. We need to allocate memory for a new node that stores the new value we want to store. You will also notice that its next node member variable is storing the address of the first node, what was the first node in the linked list. We then have to update the pointer to the list head to store the address of this new node. So how do we get to this point? Well, if pointer to list head is not equal to null pointer, there's at least one node in this linked list class. So we will create a temporary variable where we assign, which is initialized with the address of a new node. That new node will store the new value, but its next node member variable will be initialized with the current value of pointer to list head. So now the new node is storing the address of what used to be the first node in the linked list. Then we will assign to pointer to list head the value of this new node. So now pointer to list head stores the address of this first node. The first node stores the address of what is now the second node. And the second node, at least in this case, has as a pointer to the next node the null pointer. So this linked list has two nodes in it right now. Now, can we simplify this implementation in any way? Well, if you ever see something that looks like this, a local variable is initialized with a value 3.2, and then another variable is assigned that new local variable. Well, we can just replace this with that local variable y being assigned 3.2. The same thing here. We just had a local variable that temporarily stored the address of the new node, and then we assigned to list head that address. We can just replace this by assigning pointer to list head that new node. All right, so in our push front function, we have two such instances where we create something new, assign it to a local variable, and then assign a member variable that the value of that local variable. So in both of these cases, we can just simplify these to have that member variable assigned the value returned by new node. Now, some of you novice programmers may be worried about this particular statement because we have pointer to list head appearing both on the left and the right. And so you may be worried about how this is evaluated. But always remember, with an assignment, the right-hand side of the assignment operator is always completely evaluated first before the member variable on the left-hand side is assigned. So in this case, when the new node is constructed, the new value is passed, but it is the old value or the original value of pointer to list head that is passed as the second argument to the constructor. So the new node is being initialized with the new value and the current value of pointer to list head. Only once the constructor returns does new return the address of that new node, and only then is pointer to list head updated with that new address. Now note that given the condition, the consequent block of this conditional statement is run if pointer to list head is equal to the null pointer. So if pointer to list head is equal to null pointer in this case, couldn't we just use pointer to list head as the second argument to the constructor, as after all it's currently null pointer? Yeah, we could. So consequently, we could rewrite the consequent block of this conditional statement as simply creating a new node with a new value and the current value of pointer to list head, which is null pointer. So now you see something that should be rather humorous. The consequent block is identical to the alternative block. So if we're doing exactly the same thing regardless of whether or not pointer to list head is equal to null pointer, we don't actually need the condition. So here is our push front function. Pointer to list head is equal to a new node that is initialized with a new value and the current value of pointer to list head. Nice. Next, let us implement the member function front. This will return the value of the value stored in the first node of the linked list. Now, of course, if the pointer to the list head is null pointer, there are no nodes in the linked list. So we first check if the pointer to the list head is not equal to the null pointer. Well, we have the address of the first node stored in pointer to list head, so we can ask, what is the value of the node at that address? That is what we're going to return. Now, what do we do if the linked list is empty? Well, let's of course add an assertion just to make sure that another subsequent user or programmer has not accidentally made a mistake. We'll make that assertion and we will throw an out of range error. Basically, we are asking for the first entry of a linked list when that linked list does not have a first entry. Consequently, it is out of range, and we will initialize that exception with the string "the linked list is empty" to make the user aware of what has happened. Now, how can the user check if a linked list is empty? After all, the user does not have access to the list head pointer. Well, for this, we can introduce an empty member function that returns a Boolean value. And implementing this is straightforward enough. It will just simply return whatever pointer to list head equated to null pointer evaluates to, be it true or false. If it is null pointer, this evaluates to true. If it is not, this will evaluate to false, and that is the value that is returned. Now, some of you are very likely to author this function as follows. If the pointer to the list head is equal to the null pointer, then return true, else return false. This is a completely acceptable implementation as well. However, it is entirely equivalent to the following implementation. Why? Because the comparison of the pointer to the list head to null pointer is either going to evaluate to true or false. If pointer to list head is null pointer, then this comparison evaluates to true, and that is what is returned. Otherwise, it will evaluate to false, and that is the value that will be returned. Now, suppose we want to remove the first node in a linked list. Well, for this, we are going to introduce another member function, popFront. Now, it's going to be returning void. That is, it's not going to return anything. The behavior will be as follows. If there is at least one object or one node in the linked list, the front node will be removed. If there are no nodes in the linked list, this member function will simply return. As an aside, all of the member function identifiers that we have used so far and their behaviors are very close to the corresponding names of member functions of classes in the standard template library, the STL. Consequently, after this course is finished, you should already be familiar with how to use some of the features of the standard template library classes. So suppose that we do want to remove the front node. We're not going to do anything if the list is empty, so we will simply ask, if not empty, then we will remove the front node. Remember that inside a member function, if we call another member function, that member function is automatically called on the same object that this particular member function was called on. So if we pop front from an instance of a linked list class, then the call to empty is on that same instance of the linked list class. Notice that we changed a conditional check where we have the comparison pointer to list head is not equal to the null pointer to simply asking if not empty. What is the benefit of calling a member function? Well, the first is that it's much easier to read, and the member function tells you what is being compared, what is being tested. The second says, if not empty. Okay, so there's at least one node in it. The first one is slightly more cryptic. You have to understand the implementation of this linked list to know what that first comparison is. If the linked list is empty, pointer to list head is assigned null pointer. Consequently, if pointer to list head is not equal to null pointer, there is at least one node in the linked list. Notice how calling if not empty is that much easier to immediately understand what is going on and what we are testing. Also, a little bit more subtle, but let's say we decide later that we don't want to use pointers to list head. Well, in this case, let's say we adopt a different approach to storing a linked list. Consequently, the comparison to null pointer may actually become invalid. So for example, if we were to add sentinels to this linked list, you can look that up, then all of a sudden that first comparison no longer is valid. However, if we did add, for example, sentinels, we would update the empty function to account for this. So consequently, the second implementation, if not empty, will continue to work so long as we have correctly updated the empty member function. So suppose we want to remove the front of this linked list. Here the linked list head is storing the value Casey, but we'd like to remove Casey from this linked list. So what we really want to do is we want to update the list head so it is remembering the name Bailey. So essentially, to update the linked list, we just have to update the list head to store whatever the first node was originally pointing to. So essentially, we have to update list head here to store what Casey was storing as a next node, and Casey was storing Bailey. So we update list head now to store Bailey. Thus, we can pop the front node as follows. If the linked list is not empty, just assign to the pointer to the list head whatever the first node is storing in its next node member variable. Thus, we are going to start off with this linked list with 3 nodes. The linked list itself has a member variable pointer to list head that stores the value 1F1F18. At that address, we have the first node, which is right now at the bottom. Its next pointer to next node member variable stores the address BD8. That is the second node from the bottom, which is storing the value 9.1. It's storing the address of the third node in the linked list, which itself stores null pointer in its pointer to next node member variable. All right, so let's see what happens when we execute this statement. Looking at the right-hand side, pointer to list head is an address. So to call a member function on an address, we use the arrow operator. So what we are doing is, given the address 1F1F18, we are calling the pointer to next node member function of the object at that address. Well, the pointer to next node member variable is BD8, and so that is what will be returned, and that will be assigned to list head. All right. So, does anyone see any issues here? After all, list head is now storing the address of the node storing the value 9.1. Its next node member variable stores the address of the node storing 4.2, the next node of which is the null pointer. So we have indeed removed the first node from this linked list. Well, we do have a problem here, and what is it? You may remember that every single node was dynamically allocated using new. Consequently, if we update pointer to list head, we no longer have the address of this node. But that node still exists in memory. It has still been allocated. So what we've done here is we've introduced a memory leak. We have removed the node from the linked list, but that node is still assigned to this executing program. Now, does this fix the problem? Can we just delete that first node and then update the pointer to list head? To see whether or not this works, let's again start with the following linked list with 3 nodes. So the first thing we will do is we will call delete on the current value of pointer to list head. Well, pointer to list head currently stores the address 1F1F18, and so we will let the operating system know we no longer need that memory. It's now gone. Now we're going to update pointer to list head by assigning it, we're assigning it the value of what it's wait a second, it's storing 1F1F18. We have a dangling pointer. Pointer to list head currently stores the address of memory that is no longer allocated. So that's a dangling pointer. The problem is, however, the way the operating system works is the operating system may flag that memory we just deleted as being available for someone else. However, it may also just leave it there, flagged as still being allocated to this particular executing program, just in case this executing program requests additional memory in the future. Also, the information that is there is still going to be left unchanged. So 999,999 times out of a million, this will work. We will still be able to retrieve what is at that address and update it. The problem is 1 in a million times, however, this will fail, and that will cause an exception, which will then result in this program being terminated, which is probably not a desirable result. So this is not an ideal solution. Consequently, what we really want is a temporary pointer to the node we want to delete. If we have a temporary pointer to the node we want to delete, we can then update the list head member variable, and then as we have still the address of that first node, we can then delete that node. Thus, we could implement popping the front as follows. First, we're going to temporarily store the current value of pointer to list head. So we have a member variable pointer to the old head. Then we will update the list head to point to whatever that first node is pointing to for its next node. Now we can delete the old list head as we've extracted all useful information from that first node. And just to be very careful, to avoid a dangling pointer, we will set pointer to old head the value of null pointer. Now, up until this point, we've avoided implementing the destructor. Now, why do we require a destructor? Well, in this example, here data is a linked list, and we have pushed 3 nodes onto that linked list, each of them dynamically allocated. When data goes out of scope, the only thing that is lost is the instance of the linked list class, which has a single member variable pointer to list head. So that variable goes out of scope. Well, it's more or less the same as if we had the following linked list and the pointer to the first node goes out of scope. All of the other nodes have still been allocated and are still sitting there occupying memory, except now that the list head has gone out of scope, we no longer have the address of the first node. If we don't have the address of the first node, we don't have the address of the second, and so on and so forth ad nauseum. Consequently, we have a serious memory leak going on. Looking at our example, here we have a linked list with 3 nodes in it with the 3 values we indicated on the previous page. And if the local variable data goes out of scope, then we lose its member variable pointer to list head. So that is now gone. Yet nevertheless, the memory for those 3 nodes is still flagged as being allocated, even though there are no variables anywhere in the program that store any of these addresses other than, of course, these nodes themselves. But if we can't get access to one of them, we can't get access to any of them. So this is a serious memory leak. Therefore, to avoid a memory leak, it is necessary to empty the linked list first. How would you go about doing that? Well, throughout this course, we've stressed using member functions that we've already implemented or using other functions that we've already implemented. So it's actually quite straightforward to implement the destructor. You'll almost laugh. This is the easy way of implementing the destructor. While not empty, pop front. So essentially, this will keep on calling pop front on the linked list until the member variable pointer to list head is assigned null pointer. Nice, isn't it? So here's our linked list so far. We've implemented the constructor, the destructor, 2 constant member functions, front and empty, and 2 functions that modify the linked list. Push front, that inserts a new node at the front of the linked list, and pop front, a member function that removes the first node of the linked list if the linked list is not empty. Now, what other member functions could be implemented? You could implement a size member function that returns the number of nodes in the linked list. You may want to compare 2 linked lists to see whether or not they are equal or unequal. So 2 linked lists would be considered to be equal if both have the same number of nodes and the values stored in the corresponding nodes are the same. Of course, not equals would be either the 2 linked lists have different numbers of nodes, or they have the same number of nodes, but at least one pair of nodes have different member values being stored there. You might want to implement a find function, which would return the index at which a particular value is found in the linked list. And as are other functions of this variation that we've implemented, it would return a value between 0 and size -1 if the value is found, and it would return the size of the linked list if it is not found. Here, size of the linked list is the same as the capacity of an array. We may also want to implement a function that accesses the last node in the linked list. So the back function would return whatever value is stored in the last node of the linked list. Pop back would remove that last node if it exists. The clear function would empty a linked list and subsequently set the pointer to the list head to the null pointer. It's not deleting the linked list. It is simply removing all nodes from that linked list. The erase function could take an index, so it would erase the node in the linked list that corresponds to the position. So erase 7 would erase the 8th node in the linked list. erase 0 would erase the first node in the linked list. The return value would be the number of nodes that are erased. So in this case, it's either going to be 0 or 1. 0 if the index is beyond the last node of the linked list. We could also implement an erase function that takes a range. So a first index and all entries from the first index up until but not including the last index would be erased. And once again, the number of nodes that are erased or deleted would be returned from this member function. Finally, you could just implement a more whimsical function like reverse that simply reverses the order of the nodes in the linked list. Now, the easiest of these functions to implement is the clear member function, which does exactly what we currently have the destructor doing. And once this loop finishes, the pointer to list head will be assigned the null pointer. In fact, once we've implemented this function, we can even further simplify the destructor by simply having the destructor call clear. So clear was easy, but all the additional member functions we've suggested require us to in some way walk through the nodes in the linked list from the first to the last. That is, walking from the front of the linked list to the back of the linked list. We will now go through the process of how we can loop through the nodes of a linked list one by one. All the additional member functions suggested will require us to go through such a looping process in order to either access the necessary information for the correct return value or to perform the appropriate modification to the currently existing linked list. We will look at the implementation of size. However, it will be up to you to implement some of the other member functions. Again, before you go on, do consider how you might go through this process first before you continue watching the slides. So how would you go through this linked list? Well, you could initialize a pointer with whatever value pointer to list head is storing. So we'd have a local variable that would be now initialized with the value of pointer to list head. That is, it will point to the first node in the linked list. Now we can access the value at that node, and when we are done, we will update this pointer to be assigned whatever address this node is pointing to. So we'll update it, and now we're pointing at the second node. When we're done accessing this node, we will once again update this pointer to be assigned the next value, and so on and so forth, until this particular pointer is assigned null pointer, or the node in question is pointing to the null pointer for the next node. So how can we loop through our linked list node by node? As before, we suggested that we have a local variable that stores the address of a node, and we will initialize it with the value of pointer to list head. Now, while this pointer is not equal to the null pointer, we will do something. That what we do depends on what task we're trying to achieve or what return value we're looking for. At the end of this loop, we will set this local variable to be whatever the node that this local variable is currently pointing to has as its next node member variable. Notice that we can rewrite this as a for loop. So pNode is the loop variable. It is initialized with pointer to list head. While pNode is not equal to the null pointer, we execute the body of the loop, and then we update pNode to be whatever value the current node is storing in its next node member variable. Now, inside the body of the loop, we can access or modify the current node by calling the appropriate member function on pNode. However, under some circumstances, we may be required to access or manipulate the next node in the linked list. So if the next node is not the null pointer, we could even access or manipulate the next node in the linked list by having or performing or calling these member functions not on pNode, but on whatever object is at pNode's next node address. Now, something that's very important here is any one node only has access to the next node. So you can never go backward in the linked list. You can only go forward. Now, there is something called a doubly linked list, which allows you to move both backwards and forward in the linked list, but that's another topic. So for example, how do we count how many items are in a linked list? This will require us to walk through the entire linked list. So here's our for loop, and we are counting. So obviously we need some local variable that is going to record the size. So here we have a local variable list size, which is initialized to 0. Now, every time we execute the body of the loop, that means that pNode is not equal to null pointer. That means every time the loop body is executed, we should be counting that particular node. So with every single loop, we will increment the value of list size. Once the loop ends, we will just return that that local variable. Now, how do we erase the kth entry of a linked list? Once again, it's always important to deal with the special cases first, which may be easier to deal with. And always remember to reuse other member functions as appropriate. So for example, if the linked list is empty, just return 0. There was nothing to erase. However, if the index is equal to 0, we already have a member function that erases the first node in a linked list, so we will just call popFront and return 1. What do we do otherwise? Well, we must loop through the linked list, but we actually have to modify not the node that is being erased, but rather we have to modify the node that comes immediately before the node we want to erase. So how do we get to that particular node if it exists? What changes must be made to erase the next node in the linked list? And again, how do we determine if there is a sufficient number of nodes in the linked list to delete the kth node? If not, if there are insufficient, we should be returning 0. If there are sufficient, we should erase that node and return 1. Now, can we print a linked list? So for example, here I have a linked list with 3 nodes in it, and perhaps I would like to print that linked list to the screen. So I would like cout to be able to successfully print something to the screen when we pass it, or when we left shift an instance of a linked list class. For example, we are going to have the output printed as an explicit word head with an arrow indicating it is pointing to the node containing 6.5, with an arrow indicating that it is pointing to the next node that contains 9.1, and so on and so forth until the last node is explicitly shown as pointing to null pointer. You don't have to print it this way. You could instead opt to print a linked list as a list as follows. That would work too, but we're going to do the first. Now, we've already seen how to overload the left shift operator to interact with the standard cout object. So here we have a linked list. First, we will print head with an arrow explicitly to the screen. Then we will loop through the linked list, and each time we will print the value at that node, and we will then follow that by another arrow. And finally, having printed everything in the linked list, we will print the word null pointer. Notice that if the linked list is empty, we will simply have head right arrow null pointer. Now, what is the problem with this implementation? The problem is pointer to list head as a member variable of the linked list class is private, and this is not a member function of the linked list class. This is a global function of overloading the left shift operator. So it is impossible for this function to be able to access the private member variables of the linked list class. How can we fix this? Well, what C++ allows you to do is to explicitly declare either entire classes or specific functions as being friends of this class. That means a friend of a class can access the private member variables and any private member functions of this class. So it's basically saying everything is private. However, if you happen to be listed as a friend in the class, then this function, for example, can actually access the member variables of this instances of this class. All right, some of you who understand object-oriented programming, especially from languages such as Java, you might find this abhorrent. But this is not an unreasonable solution. Following this topic, you now know how to use addresses to create a linked list. You understand why it is necessary to create a linked list class, that is to prevent the user from accidentally manipulating the pointer to list head member variable. You know how to add new nodes to the front of a linked list using dynamic memory allocation. You know how to access that first node, and you know how to remove or pop that first node. You also know how to easily implement the destructor. You understand how to loop through the nodes of a linked list, and you understand the idea of friendship in C++. Here are the references, the colophon, and a disclaimer. Cheers!